Hello and welcome to the lecture on address translation. Today we're going to talk about how the operating system or the combination of the operating system and the hardware transforms virtual addresses, so the address space of a process, for example, into physical addresses, so the address space of physical memory. The main points of this lecture will be as follows. We'll first look at different approaches for address translation, and more specifically, how we can do it in a flexible way. So flexible address translation, what we mean there is how we can accomplish many things at once. We want to accomplish things like process isolation. We want to be able to have inter-process communication. We want, in many cases, shared code segments. And so on. So there are a lot of different reasons why we want this flexibility. Um, there's quite a long list of what I've been mentioning here on page 372 of the textbook. So have a look there and read a little bit about different uses for address translation and a good flexible method for that. Um, we'll also the book goes into some more advanced topics that we won't specifically cover in this lecture. Those are well, we will cover translation look-aside buffers partially, but the second point, virtually and physically addressed caches, we won't really get into that too much. But that's left as an exercise to the reader. You can have a look at that. So to start off, what actually do we mean by virtual memory? So virtual memory is generally understood as the address space um, that a process can see. So the addressable memory locations within a process's memory space. The size of this address space is dependent on the instruction set architecture. So inherently, it's dependent on the register size. With a 64-bit CPU, for example, you will have 64-bit registers, and theoretically, you have then 64-bit addressable memory addresses. But in reality, we have in practice, it's far fewer that are actually used. So even though the theoretical limit is 64, for example, AMD CPUs, we generally can virtually address 48 bits, and on Intel CPUs, 40 bits. So significantly smaller than the theoretical limit here, and the size of the register. On a 32-bit CPU, so the previous kind of generation of CPUs, there aren't many 32-bit CPUs in modern day computers these days. They may be in things like mobile phones and other smaller devices, but generally 32-bit CPUs are phased out in favor of 64-bit. So this is also, we're referring to the register size here. The CPU has a register size of 32 bits, which theoretically means we can address 32 bits of memory. But in practice, again, this is a little bit different. So for example, the Pentium Pro could actually address 36 bits of memory. So it's also dependent on the hardware. The hardware will have an address, memory address bus size. Um, and so there are many factors that actually affect the total amount of memory actually visible to the CPU. But if we take these theoretical limits, how large can our virtual address space be? So if you think of a 32-bit register, what's the largest? And we have byte addressable memory, so that means we're not addressing bits in memory, we're addressing at the byte level. So that means that we can have 2 to the 64 different addresses in a 64-bit system, or 2 to the 32. So that's quite large. In a 64-bit system, that would mean theoretically we have 16 exabytes. Um, and in the 32-bit system, you may be aware of the 4 gigabyte memory limit for a 32-bit system. So 2 to the 32 is roughly 4 gigabytes. And this discrepancy is seen between the total amount of physical memory that we typically have. So um, today's systems, we might have 8 or 16 or 32 gigabytes of physical memory. And so if we're running a 64-bit CPU, the size of the address space from 64 bits down to, say, where we have 16 exabytes of space, to where we have 16 or 32 gigabytes of physical memory. That's a huge discrepancy. Now, incidentally, this virtual address space is also the amount of memory visible to a process. So with some exceptions, the kind of legal set of addresses that a process could theoretically access are, for example, 64 bits on a, or for more realistically, 48 bits on a 64-bit CPU. On a 32-bit CPU, so 32 bits, or possibly 36 bits, depending on the implementation. So if we can address, uh, you know, theoretically 64 bits of address space, how does that map to our very small physical memory? And if we have multiple processes running on a system, obviously we can't allocate, or we can't physically have this much virtual memory and then multiplied by, say, hundreds of processes running. So there has to be some mapping between the small physical memory and the very large virtual address space. So at a very high level, the processor will be seeing virtual addresses, because these are the addresses that the process sees. We know a process is executing on the processor, so we will be executing instructions that contain different memory addresses, either loading or storing data into physical memory through virtual addresses. And the job then of the address translation is to take those virtual addresses and convert them into, if they are valid, into a physical address. So here we have in this realm, we have our, 64 or 16 exabytes possible our memory size, and here we have, say, 16 or 32 gigabytes memory size. So the job of this black box, as it is to do this translation. So we have to look at what's happening here. What kind of information do we need to store? When does the translation occur? And what happens if we try to translate an invalid address? We can see here that, for example, an invalid address would raise a CPU exception. Now, when is an address invalid? Well, an address could be invalid if we, for example, try to access address 0, or some other address that is not currently mapped into our process address space. So this exception could be something like that would, as we'll see later in the presentation, we could, for example, do a page fault here, and that would load that part of memory into our address space, and then we could use it afterwards. So the process is either doing fetching. We'll provide an address and fetch data from memory, or we'll provide an address as well as some data and write that data eventually into physical memory. So goals with address translation, as I've kind of touched on briefly, are, for example, process isolation, memory protection. We don't want to allow a process to access memory that's outside of its own process space. At the same time, we want to be able to allow processes to do this through memory sharing. So we may have shared libraries. We want to do some inter-process communication. There we need specially dedicated memory for sharing, sharing data between programs. Sparse addresses, we have processes that have multiple regions of dynamic allocation. So for example, heap, we don't allocate a heap all at once to a process because we never know how much memory a process may need. Similarly with a stack, we have this idea that we have a maximum stack size, but that may not necessarily be allocated all when the process is first initialized. So we may want to, allocate parts of memory as we go, as the program runs. We want the ability for the operating system to um, use efficient address translation. For example, memory placement. We want to be able to put parts of a process anywhere in memory so that anywhere in physical memory so that physical memory is more efficiently used. So we don't have, for example, empty space that's unusable. Runtime lookup, we want the translation of addresses to happen quite quickly. We don't want to, for example, have the time to translate an address take longer than the instructions that the program is wanting to actually execute. So this should be also efficient. And we want any kind of data structures that are going to be used with address translation to be, efficient in space and compact. This has to be looked at as well. Portability, different processor architectures make different decisions about how they approach address translation. And so within a kernel that may support multiple processor architectures, for example, the Linux kernel, we want to provide a kind of a standardized interface to address translation so that we don't have to change the kernel each time we want to, or we don't have to say make big changes to the kernel when we want to support a different architecture. We can simply have a different mapping, so a hardware independent mapping from data structures to the architecture itself. If we just have a look here at, so this is the list of Linux supported computer architectures divided up by instruction set architectures. So yeah, there are, it's supported on a lot of different systems, and all of these systems will have slightly different implementations of how, memory is managed and how address translation should happen. Different register sizes and so on. So there's a lot of different um, factors in play here, and we want to standardize this and provide portability for the operating system, the kernel in this memory translation. So one of the easiest ways to provide, for example, process isolation we looked at already is with base and bound registers. So that means each process gets a base register and a bounds register. And when a process is swapped onto the CPU, then we obviously have to update these registers so that the CPU knows when we have a valid address or not. From the processor's view, we fetch virtual memory addresses and we rewrite to these virtual memory addresses. So the processor only sees this virtual memory address space. The implementation, however, involves some hardware. So the processor it takes a virtual address, it adds to that virtual address a base register, and that actually points to the lower limit in physical memory that this particular process can address. And then it also has a bound. So if the address is beyond the bound, then you can see we raise an exception here. We don't allow the process to read beyond the bound into this space. We don't have to have a check for the base, of course, because the base is just added to the virtual address. So this is a very simple method for, accomplishing process isolation. It does have some drawbacks that we'll look at shortly, but it is a way to actually provide process isolation. Um, so with virtually addressed base and bounds, what needs to be saved or restored when we do a process context switch? Um, I actually just talked about that. So if you were paying attention, you saw that, we have this base and bound, of course. When we switch processes, these registers actually need to be updated because they are added to the virtual addresses that each process will be referencing. So basically all you need to do when you do a process switch is, along with your other registers, you need to also save and restore these base and bound registers. So the benefits of virtually addressed base and bounds, it's very simple. You see we only have two registers. We have a simple operation, and we have a simple case for raising an exception. Um, yeah, so minimal hardware needs to be added. It's safe enough, so it does what we want it to for process isolation. It can relocate in physical memory without changing the process, so that's also a benefit. And yeah, here, so we would specifically be talking about if we needed to swap a process out of memory onto disk to make use of physical memory, then we can, it's easy to, update the base and bounds to relocate that process when it's swapped back into memory. So of course we need some mechanism in the kernel to do this swapping and to update the base and bounds with the new physical memory location, but it provides an abstraction that makes this quite simple. Um, However, there are some drawbacks. First of all, we can't actually physically prevent a program from accidentally overwriting its own code. Remember, we looked at this idea of the C program's memory segments. So the instructions of a process lay here. So that's the instructions that are executed. So with a simple base and bounds, all we have is this low address and this high address, and we actually can't specify, different access permissions for different regions of memory. The text should be read-only. That should only be read by the CPU, so as instructions executed. If this were read-write, then we'd have the problem where the program could be changed while we were executing, and that can lead to a lot of problems. So we want the idea of different access permissions for different parts of memory. We also can't share code or data with other processes. This is very important. We saw this was one of our sort of goals. Memory sharing libraries, and being able to have inter-process communication. With a simple base and bounds, this isn't possible because it's actually too restrictive. And we also can't actually change dynamically the amount of memory that's used by a process. So that means we can't grow the stack or the heap on a dynamic or as needed basis. So to address this, the book introduces segmented memory. Now, segmented memory has been around for quite a long time. We take the idea of base and bounds and we actually extend that. So we keep the idea that we have a separate memory space for each process. A segment, then, we can define it as a contiguous region of virtual memory. Now this is important because in the base and bounds we're looking at adding a base to a virtual address to give us a physical address. Here we have the idea of a contiguous region of virtual memory. Each process has a segment table. So whereas we had a base and bounds register for each process with base and bounds implementation, with segmentation, each process has its own segment table. And this is very important because this will come into play when we talk about context switching. An entry in this table is just equal to a segment. A segment can be located anywhere in physical memory. Each segment has a start, a length, and importantly, an access permission. So this is what was lacking with a lot of this base and bounds. We didn't have these access permissions to, for example, have read-only code, shareable code, and also flexible memory management. And processes can share segments. So here we just the kernel just has to, mark those segments as shared between a certain process. So we have the same start length and we can have same or different access permissions depending on the process. So for example, one process could be writing to a memory location and another process could be only allowed to read from that memory location. Let's have a look at our processor versus implementation view. From a processor view, we see that we're reading and writing to virtual memory addresses. So we would have these different segments, and we can see now that they are quite similar in name to what we saw for our C program. So we have a text segment here, which would correspond to the code. We have a data segment here, which corresponds to the uninitialized and initialized data. And then we have a heap and a stack, and we see those here growing towards each other. So these segments have would have different permissions, and the processor then would access those different segments accordingly. The actual underlying implementation then is quite a bit different because we have to actually provide for how this translation happens. So the CPU sees only virtual memory, but actually we have to provide an interface to the physical memory. So what happens here? The processor sees as usual a virtual address. That is sent over the memory bus, and this is actually going through what we call a segment table. Now the segment table divides that virtual address up into two parts. We have the segment number and the offset. Now the segment number you can see directly addresses an entry in the segment table. And in the segment table we have our familiar base and our bounds. And we also have an access permission, so what can be done with that memory segment. So we fetch out of this with the segment number the base, we add that to the offset, and that gives us the start of our physical address. So that is when we see a virtual address, the segment is looked up in the table, the base is fetched, and it's added to the offset. That gives us where we actually are looking for in memory. So this provides the mapping between the virtual memory and the physical memory. Then the bound is used, of course, for raising an exception if we try to access an area beyond where we should. So that's also added to the offset, I think. No, that's just if we go beyond the bound, then we raise an exception. In physical memory, then we can see that these are our memory segments visible to the process. So we have our read write or read only that would correspond to this. We have a read write data, heap and stack are also read write. So those would be mapped in. They can actually be anywhere in physical memory. But we can see here we have base 0, that would be the code, to base 0 plus bound 0, and that would correspond, to this first entry. So we have 4 entries here, 0, 1, 2, 3, and the corresponding bases can be seen where they're actually pointing to in physical memory. So what is needed when we do a process context switch. So we're going to switch execution from one process to another, remember? Generally, when we do a process switch, if you recall, we have to save the CPU registers in the process descriptor, the process control block. We might also save the pointer to the stack and the base pointer and different things like that. The instruction pointer is something very important because we have to remember where we were executing. But if we're using segmented memory translation, address translation, then we also need to store the segment table. We need to store the entire segment table for each process. Now, these segment tables aren't very large. For example, the minimum is that we have a code segment, data segment, heap segment, and a stack segment for a typical C program. And so, a typical segment table for this simple model would just be four entries. Then we could have other entries for sharing, where we want to share code, and so on. So then, yeah, we may have a few extra segments here if the process needs to share memory with another process. So that's basically what we need. Inherently in this segment table, of course, we have the base and the bound. So there we're already saving the same thing that the base and the bound register approach was saving. And we also need to, save the other information in that table. So that's the access permissions. So recall that the Unix fork command creates a complete copy of a process. So if you imagine in physical memory, if we have one process running and we fork from that process, we will then create a complete copy of that process, and that will occupy, twice as much memory as it was before in theory. But if we think about kind of optimizations that segmented memory can give us, we can allow for a much more efficient implementation here. So the way this would work with a fork is that we copy the segment table into the child. So at this point, we're pointing to the same physical memory. We mark the parent and child segments as read-only, start the child process, and return to the parent. Remember, we get a return value from fork. So the child process gets 0, and the parent gets the process ID of the child process. If one of these, the child or the parent, writes to a segment, for example, the stack or the heap, then we can, only at that point do we make a copy of the segment and resume. So this allows us to have read-only segments up until the point where we know we need to make a write. So that write is then, we trap into the kernel with a system call, and that system call code then checks first, if we do need to make a copy of the segment, and then resume that system call. So it's a very interesting um, improvement in efficiency for this particular system call, as an example. So how does this look logically? Well, we have two processes here. We can assume that these processes have been forked. How do we assume that? Well, we see that if we look at the implementation view here, we have the same virtual address. So that sort of gives us a hint that the program is the same. And we see when we add the base for this particular process to that memory reference, we get a physical address that points here, and similarly for this process. So we know now that the code segment for these two processes is the same. Therefore, they either are a fork of one another, or they are, running the same program code. And we also see that the segments are marked as read-write here. So this tells us that either one of these programs has tried to, write to its memory space. So if we were considering before this step, all of these codes, all of these different memory segments could be pointing to the same region. But since we know that they are now read-write, and we can actually see in the physical memory, we have P2 stack here, and we have P1 stack here. So that means, one of these processes under this kind of Unix fork copy on write implementation that, we have either one of these processes has attempted to modify its stack or its heap. So therefore, we then do need to do this copy. So if a parent or a child writes to a segment, for example, the hack of the stack or the heap, we trap in the kernel, make a copy, and resume. We also have the idea of a zero on reference, and that is the case where we don't actually know how much physical memory is needed for the stack of the heap in advance. So I mean, it can grow. We see here our stack and our heap can grow as the process proceeds. So we only use how much is needed is only what's currently in use. If we need to use more, so if we try to use memory beyond the stack, then we have a case where we can we can have a segmentation fault into the kernel. The kernel allocates some more memory, so this can be predefined depending on how much might be needed. In the case of a heap, we know explicitly how much is needed because when we allocate memory on the heap, we allocate a specific amount. On the stack, we might just allocate kind of a default amount of memory. Then we zero the memory. So we want to make sure we do this because we don't want to reuse some memory that might have been used earlier, map it into our process, and then be able to read some sensitive data that was in memory before. So it's important that the kernel zeroes out the memory before it's given to the process. We just need to then modify the segment table. So to update the position of, say, the new memory segment or the updated memory segment, and then we resume the process. So the process doesn't see that anything really odd has happened, but underneath the kernel has done a lot of work to reallocate some memory for that process due to an increased need in memory. So that's segmentation. The benefits of segmentation over base and bounds should be quite obvious now. We can share code and data segments between processes. This is something that wasn't possible with base and bounds. We can protect code segments from being overwritten. So this is our text segment or our program instructions. We don't want to be able to write to that. We can transparently allocate memory as needed by the process. So the process doesn't have to know about that. And we can detect if need to a copy on write. So if we fork a process, it's very efficient when we don't copy the entire address space. We only copy that if we need to actually modify it. The drawbacks, however, we have somewhat complex memory management. We need to, every time we put a segment into physical memory, we need to find a chunk, a free space of that particular size. And it also necessitates the need to do some memory defragmentation from time to time, because as we move segments in and out of physical memory, we develop these holes or these fragments in memory. So it becomes harder and harder to actually allocate memory for certain sized memory segments. And in turn, we do start to have this wasted space between segments. So if we look here, we might have a wasted space here. So the size of a stack would not fit in here, so this isn't actually usable for a new process. Similarly here, we can imagine that this is just a bit smaller than, for example, a necessary segment for a heap or a stack, and therefore this is just wasted memory. So memory defragmentation then would go through physical memory from start to finish, reorganize it so it's all compressed neatly at the at the top of memory, and then of course update the segment tables pointing to different locations in physical memory. So we're going to see exactly how we can solve this. And we solve this with a technique called paged translation. So page translation, unlike segmented, uses fixed sized units. So with segmented, we saw that all of these contiguous segments could be of different sizes, which ultimately led to this problem of fragmentation. So if we divide these segments or these memory units up into, or these memory regions up into units of fixed size, then we essentially solve the problem of fragmentation because we know that any unit, any page will fit into any free spot in memory because all the spots will be the same size. And it also makes finding free pages easy. So we need a place in memory. We just have a list of free or non-free regions, and we can simply assign a new a new page to that region. So for example, this type of bitmap organization, we proceed as follows. We would start scanning at the beginning of our page table, and we would see here, okay, this is unused. So a 1 represents used, 0 represents unused. So we immediately see that this is a free page, and we can allocate that to, for example, a new process. Then we might need 4 pages, so we could allocate these 2, and then these next 2 that come later. So each bit here represents one physical page frame. And these pages can actually just be anywhere in physical memory. We don't need to have these memory regions contiguous as we did with a segment. So you see the stack of P1 is contiguous here. It runs from the base to the bound of this particular segment. In a page, then we would divide this up into small pieces, and you could fit part of a P1 stack down here, for example, anywhere. So they don't have to be contiguous anymore. So that's also a bonus. Um, so what do we need in terms of per process? We need, instead of a segment table per process, we need each process to have its own page table. So we're just replacing the segment table with a page table. Much like we just replaced the base and bound from the base and bound approach, those registers with a segment table when we moved from base and bound translation to segmented translation. So you can see we're building on our idea of memory translation bit by bit here. We're addressing shortcomings that have shown up. And this is a bit analogous to how memory translation or address translation has proceeded over since the 70s or 60s or 70s when computers started to become more and more common. So each process has its own page table. This is stored in physical memory. So this could be, for example, part of a process control block or pointed to from the process control block. We also need, of course, hardware registers to point to the page table start and the length of the page table. So this, in order to find the page table, obviously we need some pointer in, for example, the process control block to point there. If we look at the processor's view of paged translation, we can see here we have a process divided up into segments. We have our code segment or data segment, heap, and a stack. The heap and the stack are growing towards each other. And then we have each segment divided up into pages. So we have page 0 through n here. And this particular page 0 would point to the first part of the code, so code 0. This part of the data page, the data segment would point to this part in physical memory. So you can see the mapping here, and this mapping has to actually be laid out in the page table for that process. So the other thing I wanted to point out was that we have this bitmap allocation, and so we can easily see uh, the free pages here. So this is all free memory, and since each page is the same fixed size for all processes, that is, when you have an operating system using paged translation, all pages are the same size, and they are also a multiple of 2. Or to the power of 2, I think it was. Yeah, page 382 talks about this. Because page frames are fixed size and a power of 2, the page table entries only need to provide the upper bits of the page frame address. And so the page table can be actually more compact than the segment table. Remember that the segment table, if we go back here, we need to store the whole base in order to add it to the offset of the virtual address. So this is a benefit of page translation. We have a more compact page table. If we then move to the implementation, remember that for each of these different figures, if we go back to segmented, we had the processes view on this side and the implementation on this side. So for paged translation here, the implementation and the processes view are just on separate slides. So that's why I have 2 slides for this. So this is the implementation then. The processor gets a virtual address. We divide that virtual address into 2 parts: the page number, which identifies the location in the page table, and the offset. And the offset is added to the frame number, which is indexed in the page table, and those two together give us the absolute location in physical memory. So what happens here? We take a virtual address. We divide it into a page number and an offset. We look up that page number. We get the frame number. So the frame number is the frame from 0 to M here, and we have, I think it was 0 to N pages. So a page references a frame number, and then the frame within that frame number, remember we're looking for uh, a byte address possibly, not necessarily a frame address. So we have to then add the offset. The offset is here in the virtual address to that frame address. And that gives us the frame will point to the beginning of this frame, and then we need the byte offset that we're looking up a word or a byte in memory, and so we then need that offset in the frame. So those two together give us the complete physical memory address. Let's look up this address, G. G resides in page 1, so we're going to go to our page table. We're going to look up page 1. In the page table points to frame 3. Frame 3 is 0, 1, 2, 3. And we see we have offset 2, 0, 1, 2. We add that to the frame number and we get 0, 1, 2. So you can see how this division of a virtual address into a page number and an offset. So we're just taking that, for example, that could be a 64-bit address or a 32-bit address, depending on our architecture. And that's divided. So depending on the size that we want our page table to be and the size of each page, we will have a different division here. And we see practically how that mapping happens with these examples here. So these are 0 indexed pages, 0, 1, 2. We see they point here correspondingly to 0 indexed frames, 4, 3, 1. So 4, 3, and 1. And we also know that since we have this bitmap allocation, if we want to allocate a new page, so we want to actually write something in this memory or use it somehow, then we simply insert that frame into our page table. So our page table will then point to this newly allocated frame. So a few questions might come up when we've been talking about paging. First of all, we've looked at what we save when we do a process context switch, when we looked at base and bound, and we also had segmented translation. So what about paging? Well, paging, we either need to save the page table or we need to save a pointer to the page table. Remember, the page table itself is in main memory. We saw that back here, stored in physical memory. Each process has its own page table. So it's enough just to save a pointer to the page table. If we were going to swap the entire page table, that's going to be kind of a costly effort on the process context switch. What happens if the page size is very small? So we saw here, for example, our page size is 4. Our frame size has to be the same size, so this is also 4. So if it's really small, then what are we going to have? We're going to have a much larger page table, right? We have to divide the same amount of memory into smaller chunks. So this page table is going to be much larger. That can be good. That will reduce fragmentation. If we have larger pages, it's going to be, harder to allocate memory if the pages are too large. But at the same time, if they're too small, we have a lot of overhead in managing a page table with small pages. So typically a page table can be, say, for example, 4,096 bytes or 8,192 bytes. They can also go into megabytes. Really depends on the operating system. Yeah, so if a page is too small, then we have a lot of extra overhead. If a page is too large, then we have some internal fragmentation. We could allocate a page and only need a few bytes of that fixed size chunk. So, the utility of a large page is reduced if we only need a small amount of that memory. So how can we handle this copy on write that we looked at with segmented translation? Well, it's just as easy with page translation. If we want to share memory between processes, we can set entries in both page tables to point to the same page frames. So if we go back to our example here, we had two different processes. They would each have, and they wanted to share this frame. They would both have, 4 in their page table because remember, 4 points to a physical memory location. So two processes would have the same page table entry, and therefore they would share that memory or that physical frame. We do need a way to keep track of this memory. So in order to have a reference count, who is actually using that shared frame? So we need what's called a core map, just another data structure to manage the frames, tracking which processes are pointing to which page frames. So this is a type of reference count. That means if no one is referencing that frame, then we don't need that frame anymore. What about Unix fork with copy and write, for example? Then um, so we can do the same thing. We copy the page table of a parent into the child process, similarly as we copied the segment table. We can mark all pages as read-only and then trap into the kernel when one of those tries to write. So either the parent or the child tries to write. It's very similar to how segmenting works. Then we copy the page. Remember, this is more efficient because we're not copying the entire segment, just the page. We mark both of them as writable. So now both the parent and the child can write to their respective separate pages, and we resume execution. So this lets us share our memory until share the same memory until the point in which one of them needs to write to that memory. Another thing we can do with paged translation is we can fill on demand. So we can start running a program before all of its code is in physical memory. And how do we do this? we set all page table entries to invalid. When a page is referenced for the first time, we kernel trap. That kernel trap brings the page from disk, so from the location on disk where that, say, executable is. Then we resume execution, and those instructions inside that page are now physically in a frame in physical memory. The remaining pages can be transferred in the background. So a kernel thread could be loading the remaining pages for a program while we're beginning to run a program without the entire program first being in memory. So this is a very useful and efficient way to start programs quickly without loading the entire program all at once. Paged translation is an improvement over segments translation, but it still has some shortcomings. We may want many separate dynamic segments. Some memory management engines use per processor heaps. You can look up the Hoard allocator if you want to, HOARD, if you want to read about per processor heaps. We know that we generally want per thread stacks because if we're running multi-threaded processes, we want those threads to be able to context switch. We often want memory mapped files. Now this is where say a large file on disk is mapped into memory, and we can then reference that memory through pages. This is an efficient way, for example, to read from page at a time a very large file without loading the entire file at one time. Also dynamically linked libraries. So these are linked in at runtime, and so this is another example of a dynamic segment. The other issue is what if the virtual address space is very large? So in the case of 64 bits, for example, if we have 4 kilobyte page size, we might have 4 quadrillion page table entries. That's obviously going to be a lot of overhead for our memory system. In 32 bits, for example, the page table entries would be around 500,000. So if the performance of paged translation is actually quite dependent on the size of the virtual address space. The larger the virtual address space and the smaller the page size, the more page table entries we need. Yet, on the other hand, if we have a large address space, virtual address space, and a large page size, then remember we have this problem. We have, maybe a more manageable page table, but we have the problem of wasted pages if we're only using a small amount of a large page. That's essentially internal fragmentation. That is wasting memory. So to address this, we move one step farther, and we're not going to visit this too deeply in detail, but suffice to say, this starts on page 385, multi-level translation. This is essentially just combining for example, segmented translation with paged translation, or having multi-level paging where you have multiple levels of page tables. So these are kind of more hierarchical approaches that attempt to actually address this issue of sparsity in the virtual address space. So we would, for example, have a tree, a hierarchy of translation tables, paged segmentation, for example, multi-level page tables, multi-level paged segmentation. So you can read about these in the following pages. I think it started at 385 from multi-level translation. But simply put, we have a fixed sized page as the lowest level unit of allocation. That's important because we don't want memory fragmentation. We then have, so this gives us efficient memory allocation compared to segments where they're contiguous. Efficient for sparse addresses compared to paging because we have these, multiple levels. Efficient disk transfers for example, memory mapped files. It's easier to build translation look-aside buffers. We're going to look at TLB's translation look-aside buffers next. Efficient reverse lookup. So if we wanted to take a physical address and figure out the virtual mapping to that. And variable granularity for protection and sharing. So, this allows you to, for example, mark the highest level of a tree as shared or read write or something, and all of the pages or the tables under that hierarchy would also inherit that protection. On the other hand, you can then also specify that at a fine level which ones under that hierarchy are for example, read write or shared or so on. So let's look at page segmentation because that's kind of one of the most common improvements. Process memory is segmented, of course, we know that. The segment table entry has a pointer to a page table, not a pointer to a segment in physical memory. And the page table length is the number of pages in that segment. So we can quickly see that if we look at the implementation here, we have divided the virtual address into a segment, a page, and an offset. The segment points into the segment table, which gives us a page table. So we have a whole page table under that segment pointer. And then we take the page number from that virtual address and we point to the frame that's in physical memory. So we can see there's two levels here of a hierarchy. This gives us access permissions. In our page table entry, we have of course, the page frame pointing to physical memory and the access permissions. So here we see we have already two levels of access permissions. One, high grain or coarsely grained access permission. So that could be here. So that could mean that all pages under this page table are read, or we could then set one of these to read write, and so all of those except would inherit their parents' access permissions. And sharing and protection, can be at either the page or the segment level. So as I said, the hierarchy of access is either coarse-grained or can be fine-grained. So similar to the other approaches, what do we need when we do a process context switch? Well, since we are hierarchical here, we can simply store the segment table per process. And again, that's usually done in hardware. So similar to the segmented approach. And this will allow us to, have if this structure is saved in hardware per process, then we are able to, perform a context switch. Simply swap out this table, and then we have the pointer to this indirect pointer to our physical memory through pages, as we would have. The kernel should be portable as possible, and that means abstracting away from different hardware implementations of the memory subsystem. So we know that some parts of the virtual memory subsystem are in hardware. There is, for example, when we if we copy over a process context switch, the segment tables are copied from the process descriptor or main memory into the hardware tables, for example. And the similar with the page tables. So we would actually want some hardware implementation of these currently active page tables, so that the lookups are much faster. So the kernel essentially needs to rather than rely on different architectures for managing this information, such as where in memory the segments are, and so on. The kernel will have sort of a duplicate of some data structures. So we need to know a list of memory objects, so the segments that would be parts of different process images. We need to know the mappings, so these are the page tables, the virtual page to the physical page frame in physical memory. And often when we want, say, a reference count, as I mentioned before, we would want a reverse mapping, so a physical page frame, which individual pages are using this physical page frame. So that would allow us to say, share, for example, process code between multiple processes, and when one of those processes exit, we could then check if any other processes are still using that code, and if not, then we can free that memory. Mac OS, the Mac OS has an approach called an inverted page table, and this is basically a hash from a virtual page to a physical page. And so this is hash tables are supposed to be uniformly distributed. So that means if you divide your hash space into buckets, the buckets should fill uniformly, basically independent of the input space. So with the input space here being the range of virtual addresses. So we hash from virtual pages to physical pages, and we have this kind of a uniform distribution over the hash buckets. It's also space proportional to the number of physical pages. So remember, if we have very small page sizes, we'll have a huge number of possible pages. So the page tables can grow very large for a process, for example. So this is also an approach which is used to mitigate that to some extent. We're now going to talk about efficient address translation. So we've looked at, for example, different methods for translating virtual addresses into physical addresses. And if we do this a lot for a particular process, we're going to have to it takes some time to do this translation. It's not kind of a free activity. So we introduced the idea of a cache that will basically hold recent translations between virtual pages and physical pages, physical frames. This means that we need some hardware to implement this cache, so it has to be a small piece of very fast memory. And it will essentially hold a table of recently used translations. If we have a cache hit, so that means if we find the virtual address that we're looking to translate in the translation look-aside buffer, the cache, then we have a so-called cache hit, and we use that translation. So we just take it out of the memory directly, the cache memory directly, and we can use it. So this will be very fast. A cache hit is a good thing. We found what we're looking for in there. Generally, caches should have information we expect to have in the near future. And the alternative is we have a cache miss, in which case we just revert back to our regular virtual to physical page translation. The cost of the translation then is the cost of the TLB lookup. So the lookup in the cache, how long does it take to actually access the cache and check if what we're looking for is in there, plus the probability of a TLB miss. So, what is the chance that what we find in there is actually in there, or in this case, isn't in there, multiplied by the cost of a page table lookup. So this is just this turns into, a probability of that miss multiplied by how much time that takes, and this will give us an overall sort of an average cost of lookup. That will be implemented something like this. So we have the processor giving virtual addresses. This will be sent to the TLB, the virtual address. The offset will be sent as we normally do. So the offset will be copied directly, and we will wait for either a TLB hit or a page table lookup in the case of a miss. So if we miss, we go through the page table lookup, and then the same happens at the end. We append the offset to the frame number, and that gives us our physical address in memory. That data can be then um, passed back to the processor. Of course, yeah, we still have this exception in the case that we access an invalid memory address or try to access a page table that might not be there. In which case, that page table would be loaded from disk, that page entry. So let's look at the TLB a little closer. We have our virtual address is divided into the page number and the offset. The page number is compared to the virtual page entry in the TLB. From there, we get a direct page frame, and that can be added to the offset. We get the physical memory address. These comparators can be done, for example, in parallel. So this is a small enough memory that this is possible. And if we don't have a match, then we do a normal page table lookup. As we understand with memories, generally, for example, this TLB, it's a very small cache, a very fast memory. Generally, the bigger the memory, the slower it is. So we can take the example of, an L1 cache is very close, or it's very close to the core, the processor core. And as you get farther and farther away from the processor core, the memories get slower and slower. So we have a memory hierarchy, which provides us with the illusion that we have an nearly infinite, and nearly very fast memory. But the cache and memory hierarchies have to work very very well in order for this illusion to be kind of true. If we don't have the correct things in the cache when we look for them, that means we're going to have to wait more time to go to main memory, or the bigger, slower memory that's below that cache in order to look there. And so it's always beneficial to have the correct things in the cache, the things that you expect to use. So we have this idea of spatial and temporal locality, basically meaning things that have been used in the past will tend to be used again recently in the past will tend to be used in the future, and items near other items which you are looking for example, memory addresses, will tend to be used in the future. So you have this idea of temporal locality and spatial locality, and these should be predicted well to be in the cache so that you have them when you need them. A little bit of a look at the kind of speeds and sizes of memories. First level L1 caches or first level TLB can be very fast to access but very small. And as we go down the hierarchy to larger and larger memories, you can see we're getting larger and larger here. The access times increase. Also, the cost decreases generally. So very small memories, you could pay a lot more for per megabyte, for example, than for very large memories. And we can go all the way down to disk, data center, and remote, network-based disk. So the latency and the hit cost grows as we go down. So when do TLBs work and when do they not work? What happens when we need a context switch? Do we simply reuse the TLB, or do we have to discard the TLB? Remember that the TLB is populated per process, so it contains the virtual addresses of a certain process that's currently running on the CPU. And if we were to swap that process for another one and not flush, so not discard the TLB, that would mean that the new process would have access to some of these memory mappings. And so we could figure out some information about a process or a memory space that isn't ours, that we shouldn't actually be figuring out. So basically what we need to disable that data for that particular process. And the solution to that is to have include an entry in the TLB, which is just a tag containing the process ID. That means we have a TLB hit only if the process ID matches the current process. And that'll look something like this. We have the processor, our virtual address coming from the processor. We have our page number and our offset. We have this comparison with similar to the last TLB we saw, but we also have the process ID coming in here. And this is actually has to be matched along with the page number in order to get a hit and get the frame number. So this translation look-aside buffer here will contain the virtual addresses of many processes, and they are, of course, indexed by the process ID. So there, that has to match along with the page number. And then if those two items match, we get the direct, physical location. The frame number and the offset is copied directly. So we've covered quite a bit here. We've looked at extending the idea of memory isolation through base and bounds, base limit registers. This method allows us to have process isolation. We can keep a process from touching anyone else's memory or the kernel's memory. This is kind of one of the most important underlying principles of an operating system. We can also, we saw with segmentation, memory segmentation, we can allow inter-process communication, so that this segment tables allowed us to share memory regions and have some degree of access permissions on those. That also goes for code segments, so we could, for example, share dynamically loaded libraries, share programs, instructions that are already loaded into memory. Program initialization, when we moved then to the paged memory model, then we had this idea that we could load pages, bit by bit. So we would we would load a page from a program, the first page, for example, start running that, and then load any pages on demand that were then required, as we progressed through the instructions of the program, we would acquire more pages. The kernel can also background load these pages, so they kind of load transparently and in the background while our process is running. Dynamic memory allocation, so the combination of a segmented paged approach allowed us to have these the idea of dynamically allocatable heaps and stacks. So we may not we may not allocate a process the entire stack memory at the beginning if it's not going to be used, but as that process uses stack space, we could dynamically allocate new pages to that stack. And because the pages are all the same size, unlike segments, which can be long contiguous parts of memory, it is very easy to find free places for memory allocation. So we know that we can just allocate pages because we just have to find a free spot instead of searching for a free spot of memory that matches the potential segment size. So address translation allows us to do a lot of other interesting things. We saw some of these. Program debugging is another one. So we can set data breakpoints when an address is accessed. And this allows us to break on program execution and examine what's happening in memory. So if a memory address changes, then we know we've possibly executed some instruction to update that data, and we might be able to find out more about problems with our programs. Zero copy I/O. Here we can directly copy an I/O device into and out of user memory. So this is very useful when we just want to, for example, map a I/O space into memory. Then there's no expensive memory transfer cost. Similarly with memory map files, if we map a file into memory, it means we are letting the kernel use the virtual memory system to basically dynamically load pages from that file in a way that we can, for example, we can edit a very large file without loading the entire, it could be like 8 GB video or something. We could be editing that video without loading the entire video into main memory. So memory mapping is a very useful tool that's enabled by virtual memory and address translation. Demand paged virtual memory. Also, we talked about this memory hierarchy, the illusion of near infinite and very fast memory, which is backed up by a disk or memory on other machines or the network. So here we're basically allowing the programmer to use memory without thinking too much about the hierarchy. Of course, the hierarchy has to function well. The caches need to have the information we expect them to have. So this we have to use temporal and spatial locality quite efficiently in order to predict what should be in the cache, or if the cache is full, what should be ejected from the cache to load something new in. So that's all for this lecture. Thank you.